The parlor game hides a superpower. 20 questions. Yes or no answers only. I think of a thing, you interrogate. Played casually, it feels like luck. Played perfectly, 20 questions can distinguish one object out of 1,048,576. Why that oddly exact number? Because a perfect question cuts the remaining world exactly in half, and 20 halvings is 2 to the 20. 1,048,576. That one idea, questions as halvings, information as a countable quantity, launched the information age in 1948. Today we count it. Meet the unit, the bit. 1 bit is the information in one fair coin flip, one perfect yes or no. Is it alive? If half of all things you might mean are alive, that answer is worth exactly 1 bit. Ask, is it a specific teaspoon in Ohio? And the answer is almost surely no. You learn almost nothing. A wasted turn. The value of a question is not its cleverness but its balance. The closer to 50-50, the closer to a full bit. Information is measured by how much the answer surprises you. Make surprise a number. A fair coin, maximum uncertainty, 1 full bit per flip. A coin that lands heads 90% of the time. Mostly predictable, 0.47 bits. 99%, 0.08. A two-headed coin, 0. No surprise, no information, the flip tells you nothing you didn't know. Plot it and you get a hill, peak at 50-50, falling to 0 at both certainties. Uncertainty is information's raw material. What you already know cannot inform you. Now watch bad questions bankrupt the game. Perfect having questions. Each earns 1 bit. 20 bits finds one thing in a million. Lopsided questions, the kind where the answer is no, 90% of the time, earn only 0.47 bits apiece. To gather the same 20 bits, you now need about 43 questions. Same game, same target, double the turns, the cost of asking badly. 20 questions is really a budget, 20 bits of purchasing power, spent well or squandered. Shannon's formula averages the surprise. Entropy for each outcome, weighted surprise log of 1 over p by how often it happens. H equals minus the sum of p log p. Apply it to English letters. 26 symbols, naively log of 26, 4.7 bits each. But letters are not equally likely. E appears 1 time in 8, Z 7 times in 10,000. Run the frequencies through the formula, 4.18 bits per letter. Half a bit of every letter is pure, predictable redundancy, and redundancy can be squeezed. The squeezing machine, Huffman's code. The idea is a tournament in reverse. Repeatedly merge the 2 rarest symbols into one, building a tree from the leaves up. Read each letter's path, left 0, right 1, and rare letters get long codes, common letters short ones. Our English tree computed for real, E 3 digits, 100. T3. of 4, and Z 9 digits long. Average length 4.205 bits. The entropy floor 4.176. Within 300ths of a bit of the best any code can ever do. That floor is a theorem, not a coincidence. Shannon's source coding theorem. No lossless code, however ingenious, can average fewer bits per symbol than the entropy. Entropy is not one measure among many. It is the exchange rate between information and storage. Compress below it and you must lose data. Sit above it and you are wasting space. Huffman hugs it from above. When a theorem gives you both the limit and a machine that reaches it, the problem is not open. It is closed. English has even more slack than letters show. Read this, th_cat. You filled the blank without thinking. Context predicts, prediction kills surprise. Shannon measured it in 1951 with a guessing game. He had people predict the next letter of hidden text. Result, with context, English runs at roughly 1 bit per letter, not 4.2. 3/4 of written English is scaffolding, droppable, reconstructible. That slack is why sloppy handwriting, bad audio, and TXT-SPK still communicate. Language ships its own spare parts. The cast quickly. 1948. Claude Shannon, Bell Labs, publishes A Mathematical Theory of Communication, Entropy, Bits, Channel Capacity all at once from nowhere. The word bit itself, suggested by colleague John Tukey. 1952. Robert Fano assigns his MIT class a problem, find the optimal code. A graduate student, David Huffman, nearly gives up, then sees the trick, build the tree backwards. His term paper beat his professor's own published method and became the algorithm inside nearly every file you have ever zipped. Open your file system. Entropy is everywhere. Zip and PNG, lossless. They hunt redundancy and pay entropy's exact price, no less. A file of random noise won't compress at all. No redundancy, nothing to squeeze, it is already at its entropy. JPEG and MP3 cheat differently. They discard what your eyes and ears won't miss, losing information on purpose, below the lossless floor. And when a compressed file refuses to shrink further, you have met Shannon's wall personally. Every progress bar on every download is entropy, doing arithmetic. And beyond files, password strength is measured in bits of entropy, how many halvings an attacker must survive. Machine learning trains by minimizing cross-entropy. The model pays 1 surprise unit for every wrong prediction it makes confidently. Physics got there first. Boltzmann's thermodynamic entropy and Shannon's formula are the same expression, disorder and ignorance, one mathematics. Wherever there is uncertainty, there is a number counting it. A question that halves is worth 1 bit. 20 of them, a million possibilities. Surprise averaged is entropy. Entropy is the floor under every code. Huffman's backwards tree touches that floor within a whisker. Language runs at a quarter of its face value. Your files know it. Your passwords are priced in it. Neural networks are trained by it. Shannon asked the childlike question, how much does a message really say? And the answer built the modern world. Information is surprise, counted honestly.